Today we're going to start section 5.6, which is on the trapezoid rule. Let's look at what we've done so far. In this first picture, we have a curve, and we're trying to find the area under this curve. So what we did was estimate by drawing rectangles under and over the curve and find the area of those rectangles. By adding them up, we got an estimated area under the curve. Then we found they're not necessarily curves, but the function, we can find the area by using geometric shapes that we already know the areas for. Now we're going to find the area under the curve, but instead of using rectangles, we're going to use trapezoids. If you notice with the trapezoid, the slanted end will make finding the area a little more accurate than using a straight rectangle edge. First, let's look at what a trapezoid looks like. In case you're mistaken trapezoids for triangles, this is what a trapezoid looks like. We have our height on the side here, and then we have base 1 and base 2. For our purposes, though, the height is going to be along the bottom, kind of like a base, and B1 will be on the side, and B2 will be on the other side. And then we're going to have this other right there. Now, the area of a trapezoid is similar to area of a rectangle, which is base times height, except the bases are different, so we're averaging them together. We're going to add B1 plus B2, times it by a half, and then times it by the height. So if we want to approximate the area under this curve using trapezoids from point A to point B, what we can do is cut this up into trapezoids. Let's say we cut it up into this many trapezoids, and we can label as x1, x2, and so on. What we can do is take x1 and go up to the curve and then down to point A, and we make a trapezoid. Do the same thing with x2, up to the curve, back to x1 and make a trapezoid. These tops are not necessarily horizontal, they're going to be on a slant in a trapezoid shape. And so on. Now, what is the height of the trapezoid? Well, we have 1, 2, count them out, 6 trapezoids covering the distance from A to B. So how to figure out the height would be B minus A divided by the number of trapezoids. Now the bases. Whatever the function value of the curve at point A is the first base. The next base is the function value at x1. And then the next one, the function value at x2. And you'll continue this pattern till the last base is at the function value at B. So now let's figure out the area of the first trapezoid. Area is 1/2 the height, which is B minus A over N, times B1 plus B2. And the first base was f of A, and the second base was f of x1. That is just the first trapezoid. Now let's figure out the area of the region. So we're going to add up all 6 of the trapezoids. Now all of them will be multiplied by a half and multiplied by the height, which is B minus A over N. So then we need to add up all of the bases. So for the first trapezoid, we have f of A plus f of x1. And then the second one will be f of x1 plus f of x2. And we're going to continue this pattern until the last one is f of x5 plus f of b. If you notice, the x1s are repeated and the x2s, and all of the x bases are actually doubled up because they're on the left and the right side. The only ones not doubled up are the n's, f of a and f of b. So we're going to simplify the area of the region. So the integral using trapezoids formula will be 1/2 b minus a over n, and then we have f of a, and then we have 2 of all the inner ones, 2 of f of x1 plus 2 of f of x2 until we get to the end and we have 1 of f of b. And that is our trapezoid formula. So let's try an example. If we were to sketch the region from 0 to pi of the sine curve, sine starting at 0 and then going up. It'll drop below, but that will be at 2 pi. So at 0 to pi, it's only like that semicircle up above. We're going to cut it up into 4 or 3 lines, and we're going to have 4 trapezoids here. Cutting down like that. So now let's figure out the approximate area or the integral. It'll be 1/2 b minus a. So we have pi minus 0 over 4. That tells us the height of each trapezoid. Now, we have f of 0 one time, plus, if we have pi, and these are divided up into fourths, we have pi over 4, pi over 2, and 3 pi over 4 as our other markings. So we'll have 2 of f of pi over 4, plus 2 of f of pi over 2, plus 2 of f of 3 pi over 4, and only 1 at f of pi. And now it's a matter of using our calculator to compute. We have 1/2 times pi over 4. Now the function value at 0 is 0. The sign at pi over 4 is, if you think of your unit circle, it would be radical 2 over 2 times the 2. So this is radical 2 over 2 times 2, which is just radical 2. Sine of pi over 2 will be 1 times 2, which will be 2. Sine of 3 pi over 4 will be radical 2 over 2 times the 2 is another radical 2, and then the sign at pi is 0. And again, do these final calculations and get an approximate area of 1.896. In class, we'll attempt to do the example 2 together, and hopefully I'll be able to answer any questions you still have on this lesson.